Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will look at the normal distribution. This is a very important distribution in statistics, sometimes called the Gaussian distribution. So unlike the binomial distribution, the normal distribution is continuous. That means the sample space is uncountable. It can take any values within a range. In fact, for a normal distribution, the random variable x can take any value between negative infinity and infinity. So it can take on any real number as its value, just some values are extremely unlikely. Now, if a random variable x follows a normal distribution, we write it like this. This says follows a normal distribution, and in the brackets, again, we put the mean and the variance. So here is a sketch of what a normal distribution looks like. It's always bell-shaped and symmetrical, which means the mean, median, mode are all equal. So as I said, the normal distribution is continuous. You can see here that x can take any value at all, and it just keeps on going. So as a general rule of thumb, discrete distributions are for what you can count, like the number of heads you toss, and continuous distributions are for things that you can measure. So things like height would be continuous because you don't have to be a whole number in centimeters. You might be 178 centimeters or 178.001 centimeters. You can be any value within a range. So continuous distributions don't have a PMF, a probability mass function. That's for discrete distributions. Instead, they have a PDF, a probability density function. This is the density function for the normal distribution. It's very complicated. So this function doesn't tell us the probability. You can't just substitute a number into this function. It tells you the probability. That's because in any continuous distribution, whether normal or otherwise, the probability you take a specific value is 0. And that makes sense because there are infinitely many values. The probability that you're exactly 178 centimeters is like impossible, because it could be 178.001 or 177.9975 or whatever. So this function is just a density. It doesn't tell you the probability. So the normal distribution is just one type of continuous distribution, but it happens to be the most important. Now, in any normal distribution, it follows the 68, 95, 99.7 rule. That's all about z-scores, how many standard deviations you are from the mean. So for any normal distribution, there are about 68, more accurately 68.2% of the area is contained between one standard deviation below and one standard deviation above. So the probability you're between one standard deviation below and above the mean is 0.6826. When we're looking at continuous distributions, the way we calculate the probability of being within a range is we find the area under the curve. Now that normally requires integration, but this is so complicated, we use other methods instead. It's really hard to integrate this function. In fact, you have to use numerical integration. So in any normal distribution, 95% of the scores are contained between 2 standard deviations below and 2 standard deviations above. So this area here between -2 and 2 standard deviations will be 0.95. And as you can probably guess, this number refers to 3 standard deviations. In any normal distribution, 99.7% of the area is contained between 3 standard deviations below and 3 above. You can probably guess that for a normal distribution, and indeed for any continuous distribution, the area under the entire curve has to be 1. Now, it's important to note that the normal distribution is a family of distributions. It's not just one. The distributions are characterized by their mean and variance. So here I've shown you 2 normal distributions with the same mean that I've called mu. The one in red here would have a lower variance. So when you have a normal distribution, the higher the peak, the lower the variance. Larger variances, like the blue one, give a flatter distribution. But you can have a normal distribution for any mean and any variance. That's why it's a family of distributions. So let's look at solving some questions. Now, as I said before, calculating probabilities is very hard even with calculus. So in order to calculate probabilities, we either need to use tables or online calculators, graphics calculators, some technology like that. I'm going to show you how to solve using tables. So let's look at it with this example. Suppose the mean height of a year 10 student is 170 centimeters, variance 121. We're going to calculate the probability that a student selected at random will be first 190 centimeters tall. So it turns out that height is approximately normally distributed. So for this question, we're going to let x be the height of a randomly selected student. We're going to assume it's normally distributed, means 170, and the variance is 121, which is 11 squared. That means the standard deviation here is 11. Now, because x follows a normal distribution, which is continuous, the probability of getting a score exactly equal to a number is 0. So the probability someone's exactly 190 centimeters tall, not 190.03 or whatever, that is 0. That is true for any continuous distribution, and of course the normal is a continuous distribution. So we can't really calculate the probabilities of getting a score exactly, but we can calculate the probability of falling within a range of scores. So we can calculate the probability of students shorter than 148 centimeters. So we're calculating here the probability that x is less than 148. Now, for a continuous distribution, it really doesn't matter if this is a less than or equal to. The probability is exactly the same because your probability of being exactly 148 centimeters is 0. Now, for this particular question, we can calculate it without tables, and I'll show you why. See, when we're not using technology, we have to convert everything to z-scores. So we're going to find the z-score associated with this. So the z-score is the score minus the mean divided by the standard deviation, which is 11, square root of the variance. So that's actually minus 2. That's the z-score here. So what we've essentially done is we've transformed from a normal distribution with this mean and this variance into the z distribution, which is called the standard normal distribution. That's the normal distribution with mean 0 and standard deviation 1. So this is what the z distribution looks like. Its middle, its mean is 0. We've just found that if someone was shorter than 148 centimeters, they would be more than 2 standard deviations below the mean. So essentially, we're looking for this area here. Now, we know from the rule I went through before that in any normal distribution, 95% of the area is between -2 and 2 standard deviations. That is 2 standard deviations below or 2 standard deviations above the mean. So what that means is because the normal's symmetrical, there must be an area of 0.05 in these two combined. So it must be 0.025 here and 0.025 here. So the area under the curve is the probability. The probability that someone shorter than 148 would be about 0.025. In any normal distribution, there are only about 2.5% of scores that are more than 2 standard deviations below the mean. Now let's look at C. We're going to have to calculate the z-score again. So 2 meters, 200 centimeters, as a z-score is 200 minus 170, so score minus mean, divided by standard deviation. So we get 2.7272 recurring. It's about 2.73. So someone taller than 2 meters is more than 2.73 standard deviations above the mean. Now, we didn't have a rule for 2.7 standard deviations, only for 1, 2, or 3 standard deviations. So in this case, we need to use either technology or a table. This is what the table looks like. We're looking at the standard normal table. Standard meaning mean 0, variance 1. And CDF means it calculates the probability up to and including a certain value. So we go to our table. It's a big table, but we want to find 2.73. So we go to row 2.7 and we want to add 0.03 there. This is the number we want. So this tells us in any normal distribution, the probability of being less than 2.73 standard deviations above the mean is this. But in our question, we wanted the probability they're taller than 2 meters. We're looking for the probability they're more than 2.3 standard deviations above the mean. So if this is the area less than 2.73 standard deviations, the area above will be just 1 minus that number. And of course, that just leaves us with 0.00317. That's our final probability. So about 0.3% of people will be taller than 2 meters. All right, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.